Hello everyone, thank you so much for your presence here. Today we'll try to talk about a very technical topic related with the presence of high pressure minerals and hydrous assemblage in the Kakowa meteorite. Kakowa meteorite is an L6 ordinary chondrite. These results are a joint effort between our university at the Agricultural University of Athens, the Natural History Museum of Vienna, and the Caltech, California Institute of Technology. More details you may find in our published paper in Scientific Reports of the Nature Publishing Group, entitled Unique Evidence of Fluid Alteration in the Kakowa L6 Ordinary Chondrite. Of course, you can click on the link below in order to have a better sense or a more detailed overview of what I will present you today. Here's the take-home message. Kakowa is very unique among the ordinary chondrites. This is suggested by the presence of high-pressure minerals, indicating a very strong collision that disrupted the L-chondrite parent body, and then followed by a weak collision, which is indicated by the presence of a hydrous assemblage that have been injected into the meteorite mass. Now, in general, what is important to say here is that the meteorites present evidence of several processes that related with thermal metamorphism, with fluid alteration, with shock damage on their parent bodies. The most direct evidence of the liquid water or the fluid water in the very early stages of our solar system is best preserved by the presence of secondary hydrous minerals. Up to now, most of the secondary hydrous minerals have been identified in carbonaceous chondrites. However, here we report for first time new data on this historical fall, Kakowa, the L6 ordinary chondrite, which fell in Romania in 19th May of 1858, while the rock has been classified at a very high shock stage between S4 and S5. I will try to present you some results that document the presence of high pressure phases within the melt veins, and also, which is maybe more important for our topic, some pockets, melt pockets, that host a novel hydrous assemblage composed by hydrous minerals, and it is really exogenous compared to the host rock. This assemblage is infilling the several fractures and formed during low velocity or low energetic collision. Here is a macro photograph of Kakowa, where we see a nice straight melt vein cross-cutting the ground mass. At the right side, you see a nice mosaic, a nice backscattered mosaic of a thin section showing the studied areas within the different melt veins. There are two major melt veins on this section, one at the middle part of the section and the other at the upper part. A dust line, dust white rectangular line, shows the area that contains the pockets of exogenous material. Also, it is important to note the presence of two large chondrules delineated by fine white lines, one of them clearly cross-cut the melt vein. This is near the area called MV3. Here is a series of different images showing the presence of high pressure minerals, including ringwoodite, wachleite, majorite, and albidic joidite. Starting from the upper left, we see a nice ringwoodite in close association with Wachliite. In B, upper right image, we see a nice intergrowth of meteorite pyrope solid solution with magnesium wustite. In C, in the middle part of the left side of this series of images, we have a melt vein hosting albitic jadeite, while a glass pocket hosting albitic jadeite lamellae is in panel D. In lower left, a very nice image of orthopyroxene, a ground mass orthopyroxene, showing a nice series of socket related lamellae indicated by the white arrows, which is in contact with a melt vein. At the right side of the same image, we see majoritic garnet along with a ringwoodite in contact with a melt vein. Finally, at the lower right, a nice high pressure assemblage composed by majorite, high pressure pyroxene, jadeite, and ringwoodite is located within a melt vein. Here's a series of Raman spectra of the high pressure minerals occur in Kakowa meteorite, along with the related reference spectra for ringwoodite, wachliite, jadeite, pyrope, and enstatite. The colored lines correspond to the reference spectra, while the different lines of gray, from light gray up to very dark gray, correspond to our analysis, to the analysis of our minerals within the melt veins, high pressure minerals within the melt veins. Moreover, we see the mineral chemistry of some of the minerals that we have analyzed, especially the majorites. We have two different majorites, one which is enriched in calcium and aluminum with up to 4.7% of aluminum, oxygen, calcium oxide in the range of 1.6 to 2.4 weight%, while another majorite, which is nearly close to the pure iron magnesium majorite and member, is also analyzed. The albitic jadeite lamellae have vacancies up to 22%, with 17% of M1 side is occupied by silicon. Now, let's move on to the central topic of this presentation. Several images, backscatter images, obtained by electron microprobe, showing evidences for the exogenous material that is hosted in Kakowa. In the upper left, we have an overview image showing a fracture along the edge of a metal sulfide clast, which is filled in part with exogenous brecciated material. The spot 1 and silicate spot are areas that have been drilled for lead isotope analysis, for isotopic analysis. In panel B, another image showing a fracture crossing the ground mass of Kakowa, which has been induced brecciation of the host minerals. In panel C, a fracture that crosscuts the majorite region of MV1B area contains exogenous material, including tabular crystals of margarite. The margarite is enlarged in D. The margarite crystal is a hydrous mineral with around 6 weight% of water, and that's a lot. That's a lot for this kind of meteorite. The white squares indicate the location of NanoSIM's oxygen isotope analysis, while the white circle indicates the location of margarite Raman spectrum, which is given in the next figure. The white cross indicates the location of margarite electron backscatter diffraction analysis given also in a image of the next slide. Along with margarite, we have identified corundum, and this is given in panel C. Corundum and albite in the exogenous material that occur as subhedral to anhedral angular crystals. Spot number 2, is a second region of lead iron rich matrix drilled for lead isotope analysis. All these analyses have been performed by François Tissot at Caltech. In panel F, firelight, which is pure firelight, the iron-rich end member of the olivine, occurs in the exogenous material as angular anhedral crystals. In G, panel G, we see an enlargement of the patch of exogenous fracture field shown in panel A, while in the lower right image, there's a further enlargement of the same patch showing margarite and silica phase, as well as the general texture of angular crystalline grains consolidated in a backscatter bright matrix. Some more features of and info about the observed assemblage, including corundum, albite, firelight with a pure composition of this member, forsterite, which is a firelight component in the range of 25 to 26%. All of this occurs as anhedral to subhedral grains up to about 10 to 20 micrometers long. The margarite occurs as prismatic crystals up to 20 micrometers long, with a composition very close to the ideal end member. Now, let's see what is listed here. Here we have the data for the margarite. Okay, now the Raman spectrum of the Kakowa margarite is given in a black line, while in orange we have the margarite from the reference spectrum from a roof database. And as you can see, the predominant peaks are there. The predominant peaks of margarite are there. The mineral chemistry is very close to the ideal, and also the EBSD pattern, which is given at the lower right image, is also indexed with margarite structure. So we are certain, we are 100% sure that this mineral within Kakowa is margarite. Now, what we did here is to do some oxygen analysis on both the ground minerals, but also the minerals that are lying within the pocket, including the minerals of the exogenous assemblage, the hydrous assemblage. In this diagram, we have two axes. On the x-axis, we have the oxygen 18, while the oxygen 17 is in vertical axis. Also, we have two lines, the carbonaceous line along with the terrestrial fluctuation line. Also, we have some other data, including the ESOL, the Eagle Station olivine, the SCOL in green box, which is the San Carlos olivine. Those two olivines are coming from a meteorite and terrestrial sources respectively, and they are used as standards. We have also a series of ordinary chondrites in gray circles for reference that have been analyzed from the same lab at Caltech, and also some analysis from olivine and enstatite from the ground mass of Kakowa, along with the corundum, albite, and margarite from the exogenous assemblage. So, one very important thing is to show what is happening with the errors. As you can see, the systematic errors are minimal because our analyses have been done on those grains that have been analyzed along with grains with very low systematic error. So all of these have been analyzed more or less together, and therefore the ground mass analysis of all the plot are plotting precisely within the field defined by the typical L-ordinary chondrite materials. This is related with a minimal systematic error. Then the detrital phases like corundum, albite, and margarite. You see clearly that they show in a cluster. So there's a nice cluster around the ordinary chondrite-like region. Now, all of our analyses are plotted above the terrestrial fractionation line. And all of these are at least 2 sigma error away from the terrestrial fractionation line. What does it mean? Our samples, our analysis correspond to an extraterrestrial material, very close to chondritic one, or based on the errors correspond to terrestrial one, because the error of each analysis is so big that could brought all of our data above the terrestrial fractionation line. So what we did is to do Monte Carlo simulation. Our Monte Carlo simulation suggests that there is 1% probability of our data arising at random from a sample of terrestrial material. That means it cannot be altogether to move from the place that are plotted right now altogether downwards to the terrestrial fractionation line. This is impossible. The most possible thing for the statistics is to have one point at the downward side of the diagram and another point going upward, and then downward, and then upward, and so on. What I'm really trying to say here is that it's impossible for all of our data at the same time to plot it downward toward the terrestrial fractionation line. So also the probability for the origin from the carbonaceous material is even lower, because the carbonaceous line is further down, further away from the terrestrial fractionation line. So that means our data have 1% probability to be terrestrial and even less to originate from carbonaceous. So what does it mean? That means there is a more than 99% probability that our data are related with a chondrite source. This is very important. This is the first kind of a margarite in ordinary chondrite that related with an oxygen isotopic signature of an ordinary chondrite. This is novel. Of course, along with the presence of the shock-related phases within the melt veins, like ringwoodite, wachleite, majorite, and albitic jadeite. The most important discovery in our research is the presence of this margarite, or in general this assemblage that hosts the margarite as well, and shows ordinary chondritic source. This extends both the impact and alteration history of L6 ordinary chondrite in general, and also drives us to say that during the very early stages of our solar system formation, where the Earth receiving a lot of material, extraterrestrial material from space, like carbonaceous chondritic material, cometary material. This material brought, of course, a lot of water in the early Earth. However, what we suggest here is that one more source should be considered by the scientists, a source which is very similar to the ordinary chondrite, and this is what brought the water, or at least a third source of water on the early Earth. Now, there are several projects in our lab that are related with meteorites. So if you want to join our lab or our research group, you may send me an email that is given on this slide. Also, within the next days, virtual course is expected to start, to announced. Will start early October. However, everyone who wants to participate, he has to complete a form, and then of course to register early enough in order to attend this course. Will be official course from our university. Some ECTS will be also granted to the participants who will successfully attend this course. Thank you so much for attending our virtual seminar for today, and until next time, you may click on like and subscribe to our YouTube channel in order to do not miss any future notification. Thank you so much.